So as I said, this is going to be in English. I think we are recording this time, so this is quite safe. My name is Andrzej Krzemieński. I work for Sabre Polska. Although I can see my colleagues, my ex-colleagues here who no longer do. And I'm here to talk about, let me go back to the first slide. I didn't realize I do something in the future about the preconditions, postconditions, invariant, function contracts, and in general about certain techniques that enable you to control the code controlling you. I have heard about the works to add contract support to the language. We will talk a bit about this towards the end. Other stuff that we are going to talk about that is applicable still today. It's more abstract and actually language. It will work back in C++ 03 or is even applicable to other programming languages. So we will go over what a function contract is. In general, we will show the distinction between a strong and a weak contract. Then we will introduce the notion of a contract violation, which is something that and help detect bugs. We'll see how constraint types can be used for enforcing contracts and preventing bugs, language support, and if time permits, we will also see what's the difference between fixing bugs and concealing symptoms of bugs. So first, function contract. And throughout this talk, I will be the vision of developing applications as this ordered sequence of steps. We start from the, we are lacking some piece of software, some logic, so we see there is a need to implement something. Then based on those needs, we choose the interface because there may be more than one way to solve a given problem. And once we solve the interface, we solve the interface, we start the implementation. You may disagree with this sequence. Sometimes it may be so obvious or some steps are so small that we don't have to think about them. Sometimes it's an iterative process, but what matters is, and this is what I'll be stressing, that there is a relation between a need and an interface. And it will come back a number of times in this talk. Start with the need. There is a need in our program to sort a collection of their weight. And as a constraint, we already have in a program a vector of pointers to aircraft. So apparently the memory is managed outside of what we see here. And here we have just shallow references to those aircrafts. And one thing we immediately observe is that gap. Like I'm talking about the aircrafts, but what you see actually in code is pointers. And this is two different things. But this is already something. Dynamically typed languages, you would get an equivalent of vector of void star, and you would call those aircrafts also. So in C++ and in strong type languages, this abstraction gap is not that big. We have class aircraft. It's a certain, this interface gives us certain guarantees. Like we are guaranteed that we can call function weight and it will return weight. Guaranteed that the compiler will force the implementer of this class to provide this function weight. And we can already use this structure. Support from the type system is limited. because the contract of our function weight here is not really complete. And again, we have an abstraction gap here. I'm talking about weight, but I have actually used, and these are two different things. And for instance, NASA learned it the hard way when they lost Mars Climate Orbiter. There were two teams. One team were interpreting numbers as newtons, the force as newtons, the other as pound forces in Anglo-Saxon units, and the effect was that it got as far as to Mars, but when we're making a descent, it gave too much thrust and was lost in the atmosphere. This unit problem. So end of the digression. Our function, we will need a function for determining which aircraft is better during sort, and we are forced on the interface like this one. The abstraction gap here. Sorting aircraft, but what we see is pointers, that is addressed to objects of class aircraft. Obviously, we will be dereferencing pointers, so we will hit on another contract. This time it will be the contract specified by the language of how we access memory locations based on addresses. And if we imagine that memory is actually a sequence of numbers, process is actually fragile. And in order to make this work, we have to make a lot of assumptions. So there is a certain expectations that a living object under this address. In case of this requirement, the address cannot have this special value null. And the only reason I call it out is that this is a specific case that actually can be checked within the language with a C++ expression. The other expectations about living objects are real expectations that could, when failed, can cause trouble, but there is no way to check them. That's one myth. Here we have another that we will work with. Way to get from the configuration an upper bound and a lower bound. They represent a close range. And in our program, we will be checking if integers that come to our program is a closed range. We devise the interface, which will probably look like this. We have function is in range, takes val, low and high. We more or less know what it does. If it's not clear from the name of the function and name of the variables, we have a comment that quite clearly. Here again, we have an abstraction gap. Closed range, which is a fairly known concept from mathematics, but what we actually see written down is two objects of type int. Huge. Contrast this with another function, f. It has exactly the same type. From the type system perspective, there are, but you can see the difference between them. From the first one, from the names, comments, we know exactly how to use it, when to use it, how the values will be interpreted, when it is correct to use this function, and what to expect from it. Function, we don't know whether we can use it now, later, what it does, how it does it. There is no hint as to what it will do. What differs the difference between those two functions is what we call the contract. Information that we need correctly. But because of how the type system works and how we have designed it, it is possible this function some values that cannot be interpreted under this contract. Like if I pass 2 and 1 to represent a range, there is actually no range here. It's just that you cannot assign a meaning of a range. So that's it for this part, and I hope that I made it clear what I mean by a function contract. It's all you need to be able to call the function correctly. It's how it interprets the inputs and outputs, what is its values may not work, and what other functions I must call before calling this function. Like sometimes it says that prior to calling this function, you have to call some global init function. This would also be part of a contract. The property here is that function contract is part of the function's interface, even if we have no features in the language or the type system directly. And the fact that certain values are not allowed and the others are expected is a consequence of this contract. And the contract belongs to a human-to-human communication. It's not necessarily something that you can express in the language. Now, a contract can be strong or weak. Let's go back to one of our functions, is in range. We said it represents a close range. And it means we can even write down in C++ the expression that tells us valid inputs. And we have to ask a question: what happens if someone calls our function like this, that the low is greater than high? How we answer this question? And one of the options would do is what we can call to weaken a contract. Rather than say we are checking that something is in range, now we put an if inside, and we are saying that this function does actually two things. Less than or equal to high, then we interpret this as a range and check if the value is in range. And otherwise, we return, say, false. So one thing we can see immediately that the comment description has grown bigger. And people do it. Why people do it and what is the motivation, because I think that I am encouraging this, because I don't. I will only show you the drawback of this. And this is it. It's weaker abstractions. Now we are, as you have seen, again, more about what this function does. We increase the complexity for no gain, because there is no use for this addition to the contract. Some sense of security or safety rather, but it's really sense of safety. We'll see why in a moment. And first, actually, and foremost, we miss the opportunity. Let's go through this list one by one. By weaker abstraction, I mean that this function talking about the range. Like now, I say, in order to express what this function does, I use just low-level operations on integers. I say if low is less equal than high, then something, otherwise something. We are not just talking about ranges anymore and being in range. We're talking about operations on ints. And we force ourselves and our callers to go lower level when they have to understand what this function does. And this alone encourages bugs. We increase complexity, because this if comment will also be reflected as an if statement inside the code. There is more code inside, more places where we can plant bugs, more things that we have to test, because now we have committed to doing this, returning false in certain situations, and nobody needs it actually. Would I ever call this function with null and check whether it is null? now I'm showing you another function with that wants to protect against null pointers. Nobody will put null pointer on purpose here, so there is no point in. We would provide an interface that satisfies no practical use. We can protect, whatever that means, against null pointer being passed here and give some sense of this whole thing safe against other values. Like, what about the FFFF value or any random value altogether? It can also be a bad value that falls out of contract, but we don't protect against it. So the user anyway has to be aware that fragile things. And finally, there is one reason why, back to my range limit, lower than the lower limit. This is when I plant a bug in my code. Like here, I confused the order of arguments. I thought that the val should go at the end, but in fact it goes at front. So I just missed the order of arguments. If is in range just provides some semantics here and just returns value false, I would never have chance to detect the bug because I never wanted to know here. I wanted to type something else. And I would rather that this function is in range helped me detect that I have a bug here. Same in positive terms. If you use strong contracts, you get better abstractions. Better because they are simple. You can just say in plain, I'm in the range of 2 integers. I'm in aircraft. It's only because it's simpler. Like we need to simplify things because the software is complex enough already. Additionally, we can help detect bugs if we keep track of our strong contracts. In weakening contracts, I would encourage everyone to look for language features and other methods to enforce the strong contracts so that we can employ them to help us. Such tools is to our example with aircrafts. We get 2 pointers which we interpret as. It is not unlikely that the implementation of the function will and here we will need to use a language feature which is called pointer dereference. And it is subject to the same rules. It starts from the need that people have address and need to turn it into access to memory. It is satisfied by the interface, which comes with a contract, a language contract in this case. Is under this address, the user has made sure that there is a valid object living, still alive. And a special case of this, that this address is not null. It's a contract in the language, so we all know the specification, to some extent, specification of the language, but the compiler vendors do know the specification of the language. IDEs know the specification of the language. All the tools can, if they want, know the specification of the language. They can like this, a runtime check like this. And in fact, when you're using a newer compiler with a undefined behavior sanitizer, it can inject this code for you. Language contract is publicly available and standardized. Another use that we can make of this part of the contract that is checkable, like analyzer. Like if we make our function inline, which here means that static analyzer at the call site will also have access to the implementation, to the function body. it can perform a symbolic evaluation of the program. It will not really run the program, but it will check all the possible paths that the program can take. And with a bit of luck, it can detect that there is a path in the program that causes null pointer to be dereferenced. And if it does this, if it detects this, it gives you a warning, still at compile time or even earlier, to respond and to fix it before you ever ship the program to the users. Is with library contracts, standard library contracts, like std_string has a precondition and that the pointer you pass to it in constructor is not null. So if by accident I wanted to pass a Q, I passed a P, and I passed a null pointer inside, because the standard library again is something publicly available and every compiler knows what it is allowed, a tool like a compiler assisted with UB sanitizer, to inject a check like this, because we know what to expect of a strings constructor. But actually, this thing never happens in practice. UB sanitizers don't, even though they could, contain checks for standard library functions. Instead, what you often see is that the implementers of standard library will put something like an assertion inside to check for the conditions. And again, they are aware of the contract because it's publicly available. The situation is different with our functions that we write, because no tool is aware of our contracts, of our assumptions that we make. And yet, if the same mechanisms could be employed to detect bugs like this one that stems from passing the arguments in different order. Try to approximate this. Like, we are lucky, and it is not obvious that some of those expectations can be expressed as C++ expressions. And here we arrive at what contract check is. This is something we derive from the function contract. And this allows us to determine that a program has a bug, because it passed at some point, it produced values that are not expected by our contract. Condition. This is something that we express on the inputs to the function. And so far, I've been showing you only the interfaces rather than implementations of the functions. And yes, that the function interface is something that involves two parties, the caller and the callee. If we miss that and look only inside the function body, to think that since there is no undefined behavior here, because people are usually afraid of undefined behavior, there is no point in taking any special actions. My function will work for any combination of ints. Yeah, those logical expressions will always evaluate to something. But the real problem is, let's go back, that the bug we want to protect against is outside in the caller, not inside. If we know that, do something about it. On the check, now it's the inverse condition. We check if this is disallowed values, like low is greater than high, and then we can respond somehow at runtime. Condition is actually easy. The hard part is how to react, because there's actually no good reaction at this point. The program has a bug, does not behave according to what we expected of it. So can we now expect that it will do something reasonable in this tough situation? It's hardly possible. People come up with different ideas, which are not necessarily good, like the default. If our function returns void, just return immediately. If it returns bool, just return false. Return ints, give me 0. returns pointers, give me null pointer. This works under the assumption that there exists something like a default that works in all contexts. It also assumes that the caller, to caller, whether we found that the value is outside of a given range, or whether we found that we cannot actually compute the value. To know which of the two it is. You may think that anyone is only interested if something is in range and only positive, expect only positive value here, but there may be other situations. For instance, we may be interested in value is within some danger zone. I used the name danger to stress that there may be something dangerous here. And the critical situation that we are looking for is whether we are outside. If we are outside of some range, it's good for us. We know that the aircraft is safe, whatever that means. And we want the value true to be returned when we are safe, and false when danger. And now if we return false only because we didn't know how to produce a value, because I missed the order of arguments, and I say that everything is safe, now this is a crime in my book. So another thing that you might think is a good idea is to throw an exception. It has some positive effect because it skips all the rest of my function. This is how exceptions work. And it also, in the case like this where I confuse the order of arguments, it will skip the caller as well. The entire part of the program that has a bug is skipped. And in some situations it works, but it's only in some situations. And it works under the assumption of catching the exception is after the bug, is outside the scope of the bug. But we can, in a way, a throw expression is only a control statement that gives the control of the program to some other place. And maybe it's in this other place that the bug originates from. Like, consider this caller. The arguments in correct order. First, the lower is always 0, and the upper is either 100 or something bigger. Now, can in this call range ever observe that the precondition is not met? Of course, it looks like it cannot, but would I ask this question? Well, the thing is, we can observe bad values even here, and this happens in behavior somewhere else in the program. Maybe the undefined behavior may have happened an hour before we call this code, or in another thread. One of the reasons for observing precondition violations is that we have undefined behavior somewhere. Maybe we're using dunking pointers in a completely unrelated part of our program, or we're using different things. We're doing different things with memory, or we may have a data race which produces values we would never expect in places we would never expect. The situation can also be detected by those precondition checks. And in this case, throwing an exception and catching it somewhere does not fix our problem, or even the consequences of the problem. Undefined behavior. Let's talk a bit about this. Here we have a undefined behavior. We are passing a null pointer and then try to dereference it in a function that checks which is less of 2 pointers. So what does the language has to say about it? The point of view of the language, it's a contradiction. First, the pointer dereference is used to get to the address under a specific location in memory and read the value from there. There is null means that there is no address. Those things combined together don't make sense. And because it falls out of the need, because the original need was to get to the memory, there is no point in even defining the behavior here, because nobody will ever create a null pointer and then dereference it. Well, I did it on purpose, but it's only to show you that this is wrong. But the programmer never wants it. If it happens because of a bug somewhere in the program. So we said that, or why does the language not define anything here? And first, because there is no use case here. And second, you may say, I wish there was a language where I pass a null pointer and this is safe to the reference. But what does it actually mean? Why do you need this? Why do you need dereferencing null pointer to be safe? What purpose does it serve? Other than now you will have comfort that you can pass null pointers and this is fine, which would just sanction any bugs that you produce with it. Like a right way to go. But this is about the language. But the compiled program is just a binary. And when you execute this in a binary, something will happen. There's basically two options here. That the program will actually go under this address 0, and maybe it exists. And it will fetch whatever value is there. It will fetch, interpret the bits as a number, and compare it. Because at this point there will be fairly random numbers. It will compare it to location, which is also some random values, and it will return a random result. Think that you are in a financial server that has to make serious financial decisions. If you make them wrong, you lose lots of money. You can even commit a crime by producing, because you are legally obliged to produce some results. So you can even be jailed for producing wrong results. And imagine that your program makes decisions based on random numbers. This is huge. Why will happen is the null pointer dereference will end up in a program shutdown. And this will not be done by the compiler, the operating system. And it will be done because it's a feature implemented in operating systems. The feature that protects other programs against your program. Otherwise, we would be writing over each other's memory. It protects your program from other programs that may do things like that. It protects one part of your program from another. Safety feature that someone spent a lot of nights implementing. Let's try to do the same. Is in range, we can check for the condition, and if it fails, we call abort to quickly stop the program. And it may seem like a very harsh solution and disproportional to the problem here, because we were able to produce enter, and now we are just stopping the program. The problem that we are protecting against is not in our implementation of the function. It may be fine. We are protecting the program against the bugs in the caller. No, nothing. That it really the operation it computes is really critical. And rather than giving false results, we can stop the program. And another reason is that can change. Implementations tend to change faster than the interfaces. So it's not unlikely that in the future we want to add something to this implementation, like for logging purposes, we need to do some statistics. we can maybe we are using subtraction. We think we are subtracting a smaller number from a bigger one, and we think we are getting a non-negative result. And random things can happen. But if we have abort before, there is no random things. The behavior is predictable. Before you think about the negative consequences of it, there are some positive things here. That apart from abort, the program will do no further damage to whoever. So to abort may be harsh, an upper limit on what this program, on what harm this program can do. As we change the implementation, we said that. And additionally, abort on many systems produces a core dump. So if the programmer gets their hand, he or she can find quickly what the problem was. To deliberately crash a program that is expected to run. Because the short answer to this question is yes. Even in life-critical applications, it is often a good option to crash the program that detected that it is in an invalid state. Consider a hypothetical tool that soldiers use that tells them how many enemies are there in the vicinity and where. The software that is running there has better not crash, because if it crashes, the soldier is left on his own. So this tool and this program has better work all the time. The value of this program working when it tells lies. If inside the function we observe that we cannot perform some computation, we are actually left with two choices. Either we produce some random result, like if we go to some safe which is 0 and tell the soldier, yeah, there are 0 enemies in the vicinity, you are good to go. Now we are doing harm. The soldier trusts us, he thinks that he is safe, but he's actually bound to kill. Instead, if we decide to crash the program, of course, we'll piss him off, we put him in danger, but we send one very important message. Now you are on your own. No longer help you, you have to deal with it. He will be pissed, he will be in danger, maybe he comes to get us later on, but at least with this message, we gave him a chance to survive. Let's go one step further. What we can do is to make our function inline so that the guts are exposed to the colors, and just deliberately plant an undefined behavior in our code. If low is greater than high, so it is a bug, we just dereference a null pointer, which is an obvious, unconditional, undefined behavior on all platforms. And it's not just any undefined behavior, it's one that is well understood by all the tools that we know. The purpose of this exercise is to give a hint to static analyzer, assuming that we have one. Like here, if the static analyzer can see a function call and can look inside the function body, detect that some execution of the program leads to the referencing a null pointer. Static analyzer doesn't know anything about our contracts, but it knows a hell lot about dereferencing a null pointer. So it will warn us. It will warn us about the null pointer difference, enough to give us some hint that we have a bug and we can respond ahead of time. And it seems dangerous to put undefined behavior voluntarily. Consider is undefined behavior more dangerous than having a bug in the program? They are very alike. Undefined behavior is just like a contract violation, but at the level of the language. Bug is like undefined behavior, but at the level of our business logic. But you don't have to do it like this. You can hide this. You can put macro like trap, which is actually a call to abort in most of the cases, except when we know we're doing static analysis. And only in this case, we turn it into undefined behavior. And this way we get the best of both worlds. Close to C, good old C assertions. And it's difficult to teach assertions and difficult to appreciate them, because usually when we learn a new thing, we ask a question, what do in my program? The answer for assertion is it doesn't do anything specific. It can do different things at different times. Sorry, because the goal of the assertion is to communicate the knowledge of the programmer, that this cannot ever evaluate to true at this point. This correct program. It can happen in a program that has a bug, and this is a hint that there is a bug somewhere. Declarative rather than imperative structure or a feature. And it is not the only one. For instance, C++ CPP core guidelines encourage using a similar macro expects. We have two macros, one for preconditions, the other for postconditions. But the idea behind them stays the same. We may have all these goods, these asserts, but still, if I put the arguments in the wrong order, depending on the values, I may get all those safety checks to pass fine, even though I have a bug. And it's true. This demonstrates that those safety checks detect some bugs, but not all of them. So we may need to revise our definition of a contract check. Can confirm that we have a bug, but it can never confirm that we don't have a bug in a function with tests. But we can do better than that. And you probably know this by now. In 2ints, we can create a class range that has 2ints inside. Well, this is a dedicated class like a range. Number of our problems, because now we force the user to the caller to create a object of this class. If the user now passes the argument the other way around, he gets a type system error while we compile. We will be able to compile it even. So the user will never see the problem. We have a chance to fix the bug earlier. However, this is how our function will look like. This class range will probably expose its members like low, high. Have to write an expectation, and we have to expect that this low spelled differently is less than or equal than high. So other than spelling it out in a different way, did we gain something from it? Answer is yes, because we changed a function precondition into a class invariant, which will probably look like this. It will have those two members, and it will have an invariant, is the that is guaranteed by us been created. Whenever you can observe the object, it will have, and in order to guarantee this, we cannot give direct access for the users. So those low and high will be private. They will be exposed by an interface that is either const or constrained by other means, so that you cannot just arbitrarily change those values. Even defined this invariant in C++ as another member function. And we can even check it using assertions. builds, or not necessarily test builds. So we can actually change our expectation here to say that for the input object, its invariant should hold. This is part of programming and the language, that the natural precondition for a function is that the invariance of all its objects hold. It's so obvious, we don't have to spell it out explicitly. It's just there. But it's still possible that the user, when passing the arguments to the constructor, will pass it the other way around. So we have to change the implementation a bit. Our constructor condition that L is less than equal with less equal to high. And we can check it with assertion. Now it's a more tricky because in a constructor, but we can do it with a bit of trickery here. So what we get from this is that invariant is a conditional guarantee. We guarantee that it holds only if that the preconditions of the constructors and mutating member functions have been met. So this is no longer a bug. I cannot just flip low and high, because now they go as one. But this can still be a bug. Like if I get some numbers A and B, which come from function bounds that has nothing to do with ranges, I may have made different assumptions about this. It was on the left, this was on the right, so it looked like I have to put it in the same way. I can still have a bug like this. So of course, this doesn't prevent all the bugs I have. But again, this is not the correct way to use this class range. The correct way is to propagate the uses of this class throughout different layers of the application. For instance, if I can make function bounds speak in terms of this range, it's function bounds that I have my place where the bug can exist, but not anywhere else. Because anywhere else, here I have only a range that is already created and is already by this invariant. So by this, I reduce the scope of the bug where it can occur and enter the system. And it's a very good technique whenever you can use it, but it's not like you can use it everywhere. For instance, a typical precondition on a access to vector is that the index you pass is less than size, and there is no way you can turn it into this small constrained class, because the range of the allowed values changes over time, depends on external conditions. Some part of the contracts cannot be expressed as precondition, addressed by this constraint classes. We can fix our problem with kilograms versus pounds. This double into a class. And the only purpose of this class is to have an invariant. We cannot even say that the value cannot be negative, because, well, the value of no object is negative, but we can compute a difference between two weights, and the weight difference is negative. Precondition or invariant here, but the class alone gives us a interpretation of how we want to interpret the values inside. So its constructor will be probably explicit, because we do not want accidental conversion from any double. And even have a constructor at all, and only have some static factory functions that have long names which tell actually going on here. And with this, we can fix our interface of the aircraft, and now it has a full contract without any comments. So this is the purposes, unlike what we are taught in object-oriented classes. The main purposes of defining a class, as I see it, is invariant to reflect. The invariant may not necessarily be expressible in C++. It may be like of this class lives, there is a resource allocated and not yet released. And another use case is if you want to assign certain interpretation of these values that is not obvious. Leaves us with a quite popular conditions that are obvious or quite obvious, cannot express them as expressions in C++. Like for C-style strings, this const char stars, to be null, or that cannot be null, and the array it points to has to have a 0 character somewhere. Check it. In order to check it, we would have to iterate over the array and look for 0. But if there is no 0, we'll iterate forever or an end. Likely be an undefined behavior. But again, we can address this problem by introducing an invariant. Same as before, except now we have an invariant and we cannot express it as a C++ expression, but it's still worth it with the class name in the type system that there exists an invariant. And if we populate it throughout the layers of the application, that there is no problem with nulls or pointers. But of course, at some point, we will get at the API that we cannot change that uses const char star. So our class will likely have a constructor, an converting constructor. There is another way to spell this in C++20 to say that, yes, we deliberately want this to be. And we have a precondition here. And again, we cannot express it. And there is no way we will be able to check it at runtime, but there is a chance we may check it at static analysis time. This is the first slide that I'm telling you about something that doesn't actually exist. I'm telling you about the possible future. We can imagine that a static analyzer understands the attribute symbolic. I just invented this name, not the name, but this attribute. And what we gain with this is, first, we have something that looks like a normal function. It has a name, you can call it, you can use it whenever you use other functions. It has a name that reflects what we mean. If it's ever evaluated inside an assertion, this is in order not to give false positive information, false positive alerts from the static analyzer. But when it is run during the static analysis time, this attribute symbolic is a message to static analyzer that says, do not look inside the implementation of this function because it's just a mock. This function as a symbol and compare it against other symbols that you see. With this is we can express our preconditions or postconditions or whatever, just as regular expressions. During static analysis, the static analyzer can compare. Expects this symbol. Get name doesn't return this symbol, it's just any const char star. There is a warning about the potential contract violation. The get name has a postcondition. Postcondition is a constraint on a return value. Return value doesn't have a name in the signature, so we have to introduce it artificially. And if we have the same symbol here, is null terminated, the analyzer can compare this symbol, postcondition, the symbol on the postcondition on this function, symbol on the condition on the subsequent function, they match. The warning is silence. So we have introduced a postcondition to the family. The use you can get from a postcondition is to match it, as we've seen, against preconditions of subsequent functions. And properties. Consider this declaration that has preconditions that numbers have to be non-negative, and the result will be non-negative. It selects one of the two. A postcondition is only expected to hold when two conditions are met. Our function doesn't throw an exception. Throwing an exception is actually saying that we will not be able to satisfy the function postcondition. Saying we are not satisfying it, no point. It's obvious that we won't satisfy it. And it even in the language, in the syntax, because if we throw, there is no return object. If it's there is no way to even evaluate this postcondition in any way. We only satisfy postconditions if we don't throw. Only satisfy the postcondition has satisfied the preconditions. So you can imagine that the only thing that this function does is to return us back either A or B. If either of those are negative, the function will return a negative number. And this is okay. You violated the preconditions, the postcondition to be satisfied. So now we can get if we add language support for contracts. So far, I have been showing you comments. Comments are a very useful feature. You can put a lot of information in the comments that otherwise you could only dream of. Comments are only understood by humans. You can teach one tool to understand comments and understand those preconditions, but it will be just individual tools. What we can do better is to provide a one unified language for expressing those preconditions that every tool in the world will understand. Another thing that we do today is putting text inside function bodies. And this is very good. It helps prevent damage. It helps testing bugs from running into the system. The way it works, you have to first plant a bug and execute the program with a bug, and maybe then respond to this bug at runtime. But the bugs are there, and we can do better in making sure the bugs never enter our system. Conditions, it is even worse with the macros, because we need to refer to the name of the return value. So if I create a temporary value like here, there is nowhere that this postcondition can be put. I cannot put it before the return because there is no value yet. I cannot put it after because then it's too late. We already left the function. So I have to function and make it longer. Now I produce the return value artificially. Now I put the postcondition. And now I have probably compromised the return value optimization. Worse if I have multiple return statements. Now I have to remember to put my postcondition in every place. It looks really cluttered, and I will for sure forget about those at some place. So what does language support gives us here? The syntax I'm showing you, there have been multiple attempts to add contracts to C++. There was one to add them for C++11, it failed. One for C++20, it failed. Now we are doing the third attempt. Here showing you the syntax from the second attempt. It almost looks like attributes, but they are not actually attributes. You would not be allowed to put a colon position. But what you get from them is, one, you put them in function declarations rather than definitions. And second, the compiler is required to check, to syntax check those expressions, that there are valid expressions, that names A, B are in scope, accessible, that the functions called are public, not private. So we are guaranteed that if wanted, it could execute those expressions. And because they are in declarations, the static analyzer can see them. because there are standards. Every tool will understand them now. Provide the same bug detection experience that UB sanitizers or other tools provide for for contracts of language features like dereferencing a null pointer. Our function doesn't have to be inline because the static analyzer, all the information that static analyzer needs is here in the declaration. So we all the relevant parts into the declaration and the body can be hidden. We can put those annotations in places that normally you cannot put any macros inside the class definition. That would be an invariant. That was actually not proposed for C++ 20, but it's a possible future addition. This can help other tools than static analyzers or UB sanitizers. Imagine this scenario. Future IDE, we write some piece of code. We know there is function is in range. We got the lower bound, upper bound, and we just call this with the arguments. We are doing a code review with our colleague. The code review passes because there's obviously nothing wrong with this function. But the IDE, it can read the declaration of the function, preconditions, and it can show the precondition to us. But it maps the names of function arguments onto the names that we have in this scope. As a result of this mapping, we have the following hint. This call in this context requires that upper is less than val. And it looks like nonsense because our goal is to determine whether the val is in range or out of range. We would already expect that the val is bigger than the upper limit. It should ring a bell that something is wrong inside the declaration. Probably IDE also provides this. And now we can see that the order of arguments we assumed. We did not see it before. The code reviewer didn't see it because he cannot see the declaration of the function. And even if he sees the declaration, it's in a remote part. They are assembled together, one after the other. So we can easily connect them and see that the order is wrong. So there is no static analysis, no really resources, incredible resources engaged in it, and yet it can prevent you from even typing the bug in the first place. Compiler can do checked based on those preconditions into your code. Because I see what the precondition is, I can insert the check in the caller. Sanitizer could do it now. Because now it's very similar, and the tools can learn what is our contract here. And there are obviously drawbacks, as in every feature. Already provide a way to stuff a lot of things in function declarations, like if function is no discard, constant, const-expr, override, or whatever, and patients only add to this set. That you can put arbitrary expressions inside those preconditions and postconditions. And if you combine it with the of lambdas to turn every expression into an arbitrary sequence of declarations or statements, mess with it. Like in this example, can you tell how many class members are defined in this class and what are their names? Good luck with this. And finally, luckily we have some time, I can show you curing the symptoms rather than fixing real bugs. Let's go back to our aircrafts. Consider this piece of code. We have two pointers to aircrafts. We start with null values. Then we get the proper aircraft pointers. we have a function here. We can see it on the side. Condition that given a name, it always returns a pointer to the aircraft. That is, either returns to the aircraft or throws an exception. That is the contract for the post condition. But unless it throws, it gives us a good pointer. So we get a good pointer X, we get a good pointer Y. Suppose this is a novice programmer, and he's told that dangerous. So if you see someone throws them, you have to catch them. He catches it, then he types // to do handle it. I've seen people do it many a time. And this is considered safe under some definition of safe. Because now, yeah, clearly we can still end up with null pointers. We check only one of those, and pass to this function is lighter, which assumes the pointers are not null and have it expressed in its precondition. And if we run static analyzer through it, there is a control path, even if we don't see it directly. This function is lighter being called with I null. Important observation is that the static analyzer doesn't understand bugs. It doesn't know where the bug is or cannot find a bug in the code, because this is very abstract notion that belongs to human communication. It finds the consequence of a bug or a symptom. It finds that it is not possible that a correct program could ever violate precondition or any contract for that matter. So it's only half of the job. Now the programmer is expected to investigate and take some action. So an inexperienced programmer types, yeah, if Y is null, just skip the call. And it is safe, but it's not. The warning is silenced now. But if our goal is to silence warnings or not to see any warnings, there's much simpler way to do it. Just don't run any static analysis at all. It will be faster, consume fewer resources, and much simpler. Our goal is to detect bugs, and with the we have a bug, so it will be much more difficult to find it. Instead, what the programmer should have realized is, but you cannot do it immediately. You have to devote some time to investigate the vicinity of this point, that we have a premature try catch. Like the function is lighter on those computations get aircraft. So it has to be in the same try catch block. It cannot be outside. Active action is to put this check is lighter inside the try catch. And if we put it inside, there is no point in having the if statement anymore, because the structure of how exceptions work will guarantee us that this function is skipped. Path throws an exception. But if we get there, we don't have to stop here. If we do this, there is no point in actually having this try catch block. What we will do if we take action on this to do is to rethrow the exception. This is the only right way. And if we want just to rethrow it, we may as well not catch it. We can fix it further. And now when we have removed the try catch block, there is no point in separating the declaration of the variables from the assignment anymore, because this try catch block was the obstacle here. So now we can reduce our code even further. Fixed, but also the program is cleaner. So the warning from a static analyzer is just a message to the user. Now you take your time, 1 hour, 2 hours, to do the investigation be so unattractive that you may be willing to pretend that there is no problem or to just silence the word. Smoother, those static analyzers and tools similar must try hard to avoid false positives. Programmer will be overwhelmed with those warnings, do even more work, and they will just give up. Okay, so we got to the end. That's what we talked about, which is the starting point of all this, is inexpressible in general. It belongs to human communication. You can use, in certain cases, you can use classes, these constraint types, to enforce some of them, like the interpretation of the values. And you can use contract annotations if you have them in the language, or some substitutes to express disallowed values, which are consequence of a contract, but are not the contract themselves. One thing I try to stress, and hopefully I succeeded, is that contracts annotations are not only about runtime checks. Runtime checks may be an obvious thing, but this is just the beginning. Instead, what we get is a way we communicate our intentions, what we know about the correctness of a program, and different tool can use it in unlimited ways, like tool experience as we do for language contracts and for detecting language UB. You can assist static analysis, better IDEs with this. And also the human understanding is better, because when you see this contract along with the function, it's reason to plant the bug in the first place.